I'm starting the live stream? Question mark? No, I think I am. Welcome back. This is Chill Maths on Twitch. I'm James, and the thing I do on Twitch is that I have maths lecture notes that I'm very slowly working my way through. I'm trying to understand quadratic forms as a long-term project where I very slowly read through an enormous textbook about quadratic forms. And we try and read all the proofs, and we try and think carefully about what on earth is going on. Hello, Maths 22222. Good to see you again. You ready for some non-fundamental discriminants? Might have to reread some of the stuff we've been doing before because I cannot entirely tell you what we were doing before. Hello, Mary. You alright as well? Good to see everyone back again. I'm not sure I've got any news this time. Last time it was all very exciting because we occasionally launch a new t-shirt or change something about, I don't know, the setup, but I think it's just me and the textbook today. That's the plan. Me versus all of this again. I have adjusted my bit rate though, which is not the rate at which I get bits in Twitch, but it's the rate at which I send bits of information to Twitch, which I think has made no noticeable difference to the experience, except that a small warning light on the dashboard that used to say warning now says excellent. So if this has affected your stream experience, then I'd love to know how. You're receiving slightly fewer bits every second, and boy, some of those seconds. Every second is a miracle on this live stream. It involves an enormous number of bits I have now seen. Maths 222 is reading the same book, and I am not surprised to hear that they go much faster. A dedicated person really trying almost reached the end of chapter 2. Yes, a dedicated person really trying can definitely read maths faster than, well, me doing it in 2 hours every weekend. Have you worked out your closing speed or something? It's taken me 6 months to get through 6 chapters, and you say 1 week 2 chapters. So I guess we've got maybe a couple of weeks before you catching distance, right? I don't know why I say these things. This is now just going to encourage Maths to get, catch up and then get very slightly ahead. Well, maybe that's good for me, but Hello, me Machine Rex. You all right again? Good to see you. Nobody has to buy any bits, to be clear. Right. I mean, I'm sure Amazon will be very happy if you purchase some Twitch TV microcurrency things. But there we go. 3 chapters because you're counting 0. Oh, did you read all of 0? I remember skipping most of 0. All the 3D stuff I skipped. If you're joining for the first time, we're pretty chill here. Hence the name of the thing. Well, at least I am, I think. I'm only medium trying to learn about quadratic forms, and you can really tell. As for the goal, I think we hit the goal, right? You know, I think we hit it, but then I found out that I only get, if we're doing anything like that, then it only happens once a month. So party is middle of August. We will see. And while I'm doing shout outs, I'll do a shout out to Ginger Ninja 1570. I love it when people have a number in their username, who followed 4 days ago while I was not live. Homely beverages and easily digestible knowledge sounds like the tagline for a show where somebody just mostly drinks tea and talks to chat, avoiding ever reading any textbook. But occasionally, it would seem, occasionally tricking somebody else into reading a textbook, so I'm feeling pretty smug about that. The idea that someone else knows maths is very good. Right. I've had that, and oh yes, there could be biscuits. Would this stream be better with biscuits? No, I've seen that sort of stream. People eating food on streams, I think, should probably be not allowed. There's a hot take. Oh, it's 10th of August. Yeah, oh no. Oh, of course, maybe you're doing some sort of summer school. We have talked about summer schools before. I don't know when I'm around. Oh gosh. Am I even here next week? Who knows? We're about to hit August, I realise, and August is a confusing month in terms of who is doing what, where, when. What's that? Oh my goodness, my calendar's pretty weird. Right, maybe it's all fine. At some point, the stream has hit some sort of milestone. Right, good. Okay, that's probably enough Twitch nonsense. Should we read about some quadratic forms? Previously on the show, we had diagrams like this, looking at the values that this quadratic form might take. Quadratic forms: x squared, xy, y squared, coefficients that might be 0. Add those up, that's a quadratic form. Whole numbers, please. And they give a whole number of values. And you can draw these lovely trees of the values that they take, where you imagine this is the value for 1, 0, xy, and this is the value for 0, 1, and then in each case you draw a kind of three-way split, and you do the value when you add together the vectors that you had over there. Is that it? Yeah, I think that's it. Yeah. And weirdly, that branching process reaches all coprime pairs of integers x and y. So this is a way of checking all of the inputs, but in a nice binary tree structure. We have lots of rules about these binary tree structures, and in particular, the question about whether it takes a value somewhere is the same as after you do some sort of cool transformation, the question about whether there is an alternative quadratic form with the same discriminant that takes the value in somewhere really obvious, like here or here, which you'll notice from its coefficients. This 1, 0, and 0, 1. So the question, does this quadratic form take the value 49, is the same as asking, is there a quadratic form with discriminant minus 12 that takes the value 49 in an obvious way? Which then, if you follow that through and do a tiny bit of number theory, it tells you that this is all about quadratic residues, really. It's all about asking, is there a value? Looking at the discriminant quadratic forms previously on the show. I think Rex and Mary are doing a great job of just... We're on page 183, and that's loads. Maths 2 I know is making a valiant effort to understand all the maths, probably more than me. And then second place, it's I think me trying to understand the maths, and then Mary and Rex in sort of joint third place out of people currently in chat. I think that's our rank order from, if you like, increasing chill. Right, okay. Don't say the Maths 2 is not chill. Maths 2 very chill. Welcome to Chill Maths. Okay, but tier list, but yeah, okay. Yeah, okay. Good, phew, right. This is me now. Am I trying to start a fight? Oh dear. Yeah, I know, the 1/0 stuff is a bit upsetting, isn't it? I much prefer, so we've occasionally, the book has been referring to those as fractions and writing them like this. I've been much happier to think of them as pairs of numbers, x, y, with the additional requirement that the numbers are coprime, which you get for fractions if you sort of mumble or assert that all your fractions are always written in lowest form. But I feel more comfortable casting it as a subset of R squared, rather than trying to use fractions which come with their own baggage about equivalence. I mean, it's the correct equivalence, so in some sense maybe I should be using that fraction. Does the book at one point say 1/0 is the same thing as 2/0? Oh no. Chat, stop dividing by 0. Even if the book's encouraged you to. No dividing by 0, even if textbooks try to do it to make a point. Right, here we are. Yes, there's all these facts about the conductor, which is the largest square. Is this the conductor? The largest square you can divide the number by to still get something that's 0 or 1 mod 4. Oh, I've messed up my hair now. Oh dear. Doing a kind of agony expression. So the conductor here is 2. No, so I said largest square, but I suppose I mean d squared. If d is the conductor, then d squared is the large square you remove. You remove the square 4 from 28 and you still get something that's... Sorry, you move the square 4 from minus 28. I have to pronounce the minus sign. So you get minus 7, which is 1 mod 4. Critical that I say the minus sign, otherwise I end up trying to tell you that 7 is 0 or 1 mod 4, which is not true. I will learn this, that the minus signs really matter for modular arithmetic, except for mod 2. Mod 2 you can get away with anything. It's amazing. I love mod 2. Good. Right, okay. So we had this stack of things that we tried to understand really quickly at the end of the last episode. I've used mod1 to try and explain the torus to people. You have coordinates with real numbers x mod 1, comma y mod 1. Then you get a kind of little model of a torus, depending how you think about it. It does the looping property in both directions, so I guess it's like a torus. Mod 1 is great if you look at reals. Reals quotiented by the integers. I suppose I'm saying r squared quotient. What am I doing? Reals quotiented by the integers cross reals quotiented by the integers. That way around. It's not the same thing as r squared quotiented by z squared. No, what's your action on? Anyway, never mind. Okay, anyway. Getting distracted, trying to fix it. I had this horrible thought about, I don't know, my linear algebra lecturer listening to the stream for some reason. Horrible thought. Right. Where are we over here? I can't remember why we were doing this, but for a prime p, if a product like this is represented by a primitive form of discriminant delta, then so is this. But no, sorry, not so is this. This is represented by a primitive form of discriminant this. And that feels a bit like you just multiply by p squared, but how does this proof work? K is greater than 0 in at least one of the regions adjacent, not divisible by p. Oh my goodness. Oh, I don't get it. Equivalent to a form like this. I should never say on the stream that I don't get it, because then I'm forced to go back and actually learn it and understand it. I can get away with not understanding things as long as I don't admit them to you. But in some sense, that's why you're here. What's all this? What's all this? Who was paying attention last week when we looked at it? Yeah. Good old spheres. Right. Okay. Suppose we have a primitive form of discriminant delta representing p to the kq. The top of this form has a region labeled p to the kq. With you so far? K is greater than 0, so at least one of the regions adjacent to this region must have a label not divisible by p. Otherwise a vertex. Oh yeah, this is the thing about it being primitive. So not everything is a multiple of p. In particular, not all of its values are multiples of p. In particular, is that true? So if all of its values were multiples of p, that would be bad news. Anyway, if three things around a vertex were multiples of p, then I think you can infer that the coefficients were multiples of p. The form p times some form non-primitive. Thus, the given form is equivalent to this, with c not divisible by p, where so p to the kq and c are the two values on either sides of that particular edge. Okay, so this is about doing some transformations and writing a particular form to bring that interesting edge over to the middle of the Ferri diagram, and then looking there to say, aha, left value is p to the kq and right value is c. So it's equivalent to this. The form like this, so then multiplying up p squared here and p here has the correct discriminant. So I can't just multiply. Why haven't I just multiplied everything by p? Oh, because I'm not really going for that. I'm trying to get this to be represented. I'm not trying to get p to the k plus 1q to be represented by anything. And is primitive. Oh, this is still primitive. I'm not allowed. I'm supposed to be just looking at primitive forms in both cases. This is very hard to read. Primitive form here and then primitive form here. Right. Previous form. Okay. Nor are the divisible by any other form, since prime would have to divide q, b, and c, which is the things from before. Okay. I didn't realise this would be hard to prove because I've missed the word primitive here. It's trivial if you don't have the word primitive here, so I didn't understand what the fuss was about. Yes. Okay, good. Right, we've reached the bookmark again, which Mean Machine Rex has noticed that I drew. I think this thing does have a bookmark feature, or something at least. Like I could tag it with bookmark. Would that be good? Let's tag it with bookmark. There you go. And now this page is tagged as bookmark. I just can't be bothered. So it remembers which page I was on. And it's not Chrome PDF Reader. It is slightly better than Chrome PDF, but only a bit. I have a tablety thing. It's better when I draw it. Thank you. There you go. Yeah, primitive means they have no common factor, and I missed the word primitive here, which makes it really easy to represent stuff because you can just multiply by whatever you like. And I sort of slowly realised that the thing I was trying to represent wasn't the thing I'd made. You can't just multiply through by p squared. The discriminant is non-linear in the coefficients. It's quadratic in the coefficients. So you can't just multiply by p squared. I sort of jumped from here to here and said to myself, that looks easy, without spotting that multiplying by p squared doesn't represent that. Multiplied by p actually doesn't represent that either. And also, you can't just multiply up. You're looking for a primitive thing. Pay attention. What's going on? So I think reading it was where I let myself down, because I read 3 things wrong. Reading is tricky. Matt's asked what my folder system is like. I'm not sure I can actually show you. I think it doesn't screen share when it's doing folders. I've got a folder for all of my meeting notes for meetings with other people, which I can't show you. I've got a folder for each year of the maths course at Oxford for teaching. I've got a separate folder for student work from teaching. I do things sorted by kind of job, or why have I got them, things. I quite like having quite a lot of top level folders. I don't like digging too deep through folder structures. I sort of think partly I think that folders might be overrated, but folders is how I grew up. Folders is deeply ingrained in my brain as how computers are supposed to work, that everything's in folders. You neatly file things in folders. But there's this theory that folders are overrated. You're supposed to tag everything now, so that if you want to find something, you just search by tags, and you can do and on tags. You can find things that are this quality and that quality, whereas in your folder you can't file it in both folders crisscrossy. So people who have opinions about this, I think, tend to have the opinion that tags are better than folders, but people with muscle memory like me seem to be stuck doing folders. TLDR, don't use any folders at all. Just stick them all in there. Like cloud services. Have you noticed this? If you have like a cloud service, like Google Drive or whatever, it's really keen for me to just upload files. Don't even think about it. Just stick them all on the cloud. Like, you want to put it in a particular folder? Just save it to the cloud. Turn on autosave, and it will just go on the cloud. It's not in a folder. It just you've got to use our AI search tool to find it again. Which obviously I don't enjoy. Don't sort things. Just put them all in this big bucket, and then we'll use search tools to recover the thing that you were just working on. It's like, oh no. It was also tidy. Right, so I've currently got loads of folders. I love questions. Questions are much easier to answer than reading. I haven't read any new content yet, have I? Right, good. Yes. So we're talking about Remarkables, because we're not sponsored. If they're watching, you've waited years to sponsor. We are not sponsored by Remarkable, but the thing that happened was that I saw loads and loads of adverts for them, and then I got one, and I still get loads of adverts, so that didn't work. My advice, if you're getting loads of adverts, don't think that buying one will stop the adverts. It's pretty good if your life involves a lot of PDF files. For example, if you read a lot of lecture notes and mark a lot of student work, which has been submitted as PDFs, then yeah. Then there you go. If your life doesn't involve any PDFs, then I'm so jealous of you. I'm so jealous. Enjoy your PDF-free life. Sounds lovely. Right, okay. Here we go then. Let's read on. For non-fundamental discriminants, theorem 6.11, which I've forgotten, so we're going to have a quick look to get the kind of flavour of 6.11. It was a while ago, wasn't it? Oh yeah, we did this before. We did this flipping backwards and forwards before. 6.11 was down here, and it was all of this. Oh my goodness. 1/4 discriminant. I sort of remember. Can I remember the terms and conditions? Powers to distinct primes. Each represents form discriminant delta where these things are primes dividing the delta at most one, but not the conductor. Primes dividing the conductor allowed are, oh my goodness, following rules. Following rules. And it depends about whether that prime, how much it divides that, and then also some other stuff to do with P's and Q's, and it comes from quadratic residues. For example, there's this get out clause where S is even, and S is even in even power in the discriminants, and also you need Q to be a quadratic residue modulo P. Fun stuff, just fun stuff. So there's all that mess. What's the claim? What we're about to read then? Represent at least one form of discriminant like this, exactly when n factors the product of powers of distinct primes, each of which is represented by some form of delta. Primes not divided, but not dividing delta, not the conductor. This seems good. So what's this new thing we're reading? New sentence down here. For non-fundamental discriminants, theorem 6.11 says nothing about whether the resulting forms are primitive. Read the whole sentence. Oh no. As we will see in theorem 7.7, here we saw that 222 one, didn't we, halfway through? If we... As far as it's cursed. If we see in theorem, as we will see is such a good phrase for this book, in theorem 7.7, determining the numbers represented by primitive forms of a given discriminant also reduces to the special case of representing prime powers by primitive forms. Okay, this is the same question. We're going to carry on looking at prime powers by primitive forms. N Stucky's here! Yes, hey N Stucky! Welcome back. Good to see you. People remember N Stucky, right? You'll know N Stucky. N Stucky also streams. If you're not following N Stucky, you should follow N Stucky. Good. N Stucky, I've been live for half an hour and I have read 2 sentences and I read one of them wrong. I'm doing my chill thing. Right. But we're doing a lot of representing prime powers, and we're going to see in the distant future a theorem that says that that's okay. Classic. Yeah, good. Everyone represents Stucky. Good. Represented by a primitive form exactly when each prime power is represented by a primitive form. Ooh, that's good. Okay, I want to read that again. That was fun to read. A product of powers of distinct primes is represented by a primitive form exactly when each of the prime powers is represented by a primitive form. So that's the thing again where, looking forward to theorem 7.7, I suppose, that says just looking at individual primes, as is often the way, isn't it, with number theory. Look at the individual prime powers. Some sort of general advice, I suppose. I hope you can Chinese remainder theorem your way towards the general case. I assume that's what's going to happen again. It's always that. If you're a quadratic residue modulo 2 of these things, maybe you could be a quadratic residue relative to their product. It is, isn't it? Yeah, it really is Chinese remainder theorem every time. Okay, good. I've remembered some maths from earlier in the book and I'm feeling happy about that. Okay, most prime powers, here we go, most prime powers are represented only by primitive forms, according to the following easy result. We've waited so long for an easy result. I can't wait to not understand it and feel a bit less happy. Maybe Machine Rex has got a pizza. It's that sort of chill math, isn't it? Oh, right. Can't keep getting away with this. One idea be that good. Okay. A form of discriminant delta representing a power of phi to the k of a prime p, not dividing the conductor. Oh god. Easy result, they say. A form of discriminant delta representing a power pk of a prime, that is what a power of a prime will look like, that doesn't divide the conductor. A power of a prime p of a prime p not dividing the conductor is all one phrase. It's not just me, right? This sentence is extremely hard to read. Is it just me? A form of discriminant delta representing a prime power A form of discriminant delta representing a power p to the k of a prime p not dividing the conductor of delta is primitive. It's the form that is primitive. The form... So when they say most primes, they mean, well, we're going to prove something for all the infinitely many primes that don't divide the conductor. Not dividing. So you kind of need, it's weird, you kind of need, the conductor of delta is one phrase, and you kind of need a prime p not dividing the conductor of delta. Yeah, that's the brackets that I needed. A form of discriminant delta representing a power p to the k of a prime p not dividing the conductor of delta is primitive. You pause. You could do with some like commas or something like that. Oh my goodness. Why is reading so hard? I think the maths might actually be fine. It's just reading that it's not my problem. There's a chat thread that I'm in for lots of maths people, and today's topic of discussion is whether most people's problem with maths is actually a problem with reading. But literacy is actually really important if you want to understand really technical, precise mathematics. And sometimes I come up against a sentence like this, and I worry that for me it's a literacy thing as well. Yeah, I just need a little bit. We've got all these phrases or noun phrases that you have to be able to pass as kind of a single thing. Anyway, I'm probably overthinking it now. Here we go. What is this then? Yeah, so I was going to say almost always, if you represent this power p to the k, then you're probably going to represent that prime is probably going to divide the conductor, because almost always. Yeah, okay, let's write it out. If a form q representing this is not primitive, it's a multiple of another form by some integer d greater than 1. Oh, we're doing this proved by contradiction or something. This number d divides every number represented by q. So particularly it divides p to the k, and hence p divides d. Since d divides the conductor, this means that p divides the conductor. Okay. I still need to understand conductors a little bit better. What's my working definition? I tried to say it out loud earlier. If you could take a square out of the discriminant and still get a discriminant. But I'm slightly uneasy on whether that's the same thing as saying that that number divides all the coefficients and all of the things that the quadratic form makes. I think those are all the same. But there's one of those implications I'm getting a bit worried about. So I think I might go off on one of my little tangents. I know we've only read about half a page, but I might go off on one of my little tangents just to worry that, see if I can maths this out. The thing that's worrying me is I want the following to be equivalent. I want the following to be equivalent. So if delta is d squared delta prime with delta prime, and then I guess I just want 0 or 1 mod 4 as my condition for whether or not it's a discriminant. I would like this to be equivalent to d divides x squared plus bxy plus cy squared for all xy, with the kind of given b squared minus 4ac if that's the definition of the discriminant. I'd quite like those to be equivalent facts. They don't look equivalent facts. Yeah, I agree with me, Machine Rex. Not on everything, sorry, me, Machine Rex, but I agree with me, Machine Rex, saying if you can't read the question, how are you going to solve it? So there you go. And language barrier as well, if I'm doing everything in, I mean, I'm lucky I'm doing everything in my first language right now. I say first language like I have a second language. Right, okay. Okay, so I have this other thing as well, which is like d divides a, d divides b, d divides c. Right, so out of these three facts, if you have this last one, which is the easiest one to think about, if you have this last condition, then definitely d squared divides delta. And then I haven't really thought about 0 and 1 mod 4 stuff at all. So maybe that falls apart. So yeah, I worry a bit about this. What if the leftover bit is 3 mod 4? If d squared is 1 mod 4, this is all fine, because this was 0 or 1 mod 4. The case that I should worry about is check what happens if d equals 2, d divides a, d divides b, d divides c, but delta is 4 times delta prime with, and then delta prime, well, not 2 mod 4, because then, oh, maybe that'll be fine. Say something weird like 2 or 3 mod 4. Could that happen? Ah, yeah, landing numbers. No. Yeah, I'm having trouble with the subdiscriminants. So Matsuda2 in chat says, conductor is the discriminant divided by the smallest non-trivial subdiscriminant. And I'm having a real mental block on the phrase smallest non-trivial subdiscriminant. I just want it to be easier than that. I want it to be like the highest common factor of the coefficients. I don't think that's true though. I'm going to discover why not by messing around with it over here on the side. I have all this margin space. Like, I don't know what that guy was complaining about. It just you can just scroll and then there's more margin. It's just to the side, like you get a little bit more, and then a bit more like that. I don't know. Loads of room for activities over here. I actually realised it is finite, so it is finite, so I could run out of margin space actually. Okay, good. Yeah. If you start a new document, it goes forever. But if you have an existing PDF page, it's limited. That's weird. Never mind. What happens if I try to print it with writing off the answer? Never mind. Let's not think about PDFs right now. Oh, chat! I've started thinking about PDFs instead of thinking about maths. Things have got bad if I'd rather think about PDFs. Right. So clearly, if d divides a, b, and c, then it divides this for all integer values of x and y. And then I'm worried about whether or not delta prime, the thing you get by dividing by d squared, you get from this one to this one. I'm worried about whether delta prime would really be a subdiscriminant thing with 0 or 1, that's 0 or 1 mod 4. If d squared is odd, then it's 1 mod 4, so this is fine. These things will have the same remainder modulo 4, and this one was the discriminant, so that one will be as well. Is a discriminant is, I think, just shorthand for it's either 0 or 1 mod 4. So the thing I'm worried about is this. And I think I can build an example where this happens, right? So I would need b squared minus 4ac to be 12. I'm making something that's 12 shaped by doubling all of the coefficients of something that's 3 shaped, you know, like so 2x squared minus 6y squared. Does that give me 12? B squared is 0 minus 4ac. Oh dear, no it doesn't. That doesn't give me 12 at all. That gives me 48. Chat, my even numbers have let me down. I'm going to mess around with this a bit more, sorry. B squared minus 4ac, so I kind of want them all to be even as well. Is this just nonsense? This is nonsense. I'm going to be fine. because definitely the thing that I get after dividing by d. Here we go. Yeah. So 141 is an example with discriminant 12, but not an example where d divides a, b, and c for d equals 2. The thing I'm worried about is that I have d equals 2 in each of these, and then I try to divide by 4, and I get down to 3, which is not a discriminant. But of course I'm being silly, that if d divides a, d divides b, and d divides c, then I can write out the kind of quotients like this for a, b, and c. BD and C is CD, like this. And then I've got my quadratic form looks like, well, it's this. The point I'm going to try and make here is that I know that the thing divided by 4 is a discriminant. I think divided by d squared gives me a discriminant, the discriminant of a very particular form, which I'm now going to find. It's d ax squared plus big B xy plus big B cy squared, which means that, so this quadratic form has discriminant, and it's going to look really silly now, but here we are, big B squared minus 4 big AC, which is, by the way I've constructed it, precisely delta divided by d squared. So that is a quadratic form, of course, that has a discriminant. So it must be 0, 1 mod 4, because it's a discriminant. Because it's written as a square minus a multiple of 4. So it's 0, 1 mod 4. I actually have the discriminant. I have the quadratic form that does it. I don't need to panic about getting 3 mod 4, because, well, I can just construct a quadratic form that has the correct discriminant after I've divided by d. So I think this step is also true. I think that if d divides all 3 terms, a, b, and c, in my quadratic form, then it divides all the values, which is a nice thing to think about. And you can take out a factor of d squared, and you'll be left with a discriminant of some quadratic form, precisely the quadratic form from taking out d from all of the terms. So that's pretty good. Okay. Getting there. Yeah, that's obviously what I want to do next. I think it probably doesn't, otherwise this is too neat, and we would say something different, right? Or maybe not. I would like to do the implications the other way, because quite often the textbook talks about conductors, which I think have this definition, and I would like to check that, well, I'd like to know that d divides all of the things. I don't think that way around is going to be true, because of the 141 example, I think I might need to start saying equivalent to some form or something like that. Equivalent to some form with the same discriminant. So 141 was mentioned in chat earlier. 141. No, 141 was an example for 12, sorry, wasn't it? So 12 is an example where you don't have a... So... Ooh... Mean Machine Rex has made a sphere. What does that mean? And what's it a monstrosity of a sphere? What does that mean? Spheres are some of the least useless things. So I actually think 141 is an example where the discriminant is 12, where by the definition we would say that that doesn't have any subdiscriminants, because you could try and bring out a factor of 4, but you're left with 3, which is not a subdiscriminant. So I think we're not making any claims at all about the 141 quadratic form. I guess really this is a claim about the determinant, not about any particular form. So I guess my question is, if your discriminant has a square factor and a subdiscriminant, can you always realise that? Is it always the case, and this seems unlikely, always the case that d divides all of the coefficients of any quadratic form with that discriminant? That seems unlikely. I mean, the answer is just no, right? Because you could build something with, really a really subdiscriminant prone delta, like Let's pick something where you really can take out a factor of d squared, like 16 or something. Because you can take out a factor of 4 and be left with something else. This quadratic form, 16x squared, 4x squared, 4x squared minus y squared has discriminant 16. B squared minus 4ac, come on, I can do it, minus 4ac, but not, which is just to be clear, 4, right, I mean 2 squared times 4, so it has this subdiscriminant, and it's even 4 squared times 1, and 1 is a subdiscriminant delta prime, so I think this discriminant has some conductor, but not 4 divides C. So not everything's multiple of 4 in there. Yeah, so this is an example where you can't just say all of its values are multiples of the conductor. Because, for example, 4x squared minus y squared takes some interesting values like minus 1. That's not a multiple of anything really at all. And yeah, you could do this kind of any discriminant really. So it can't really be a property of discriminants with non-trivial conductor that you can say anything about their coefficients. So the arrows go this way. That's annoying. It means that when I'm talking about discriminant, and maybe if I start talking about there is some form where D divides all the things, maybe? We were doing something like this before, weren't we? No, before we were using the arrows in the direction that they're drawn. Right, Mary in chat wants to mention that the Soma cube, the one that I've got in my office at work, is enormous. It's really big. We had it out with some small children who were visiting, and it's so much larger than the small children. So that was a surprise. I mean, not really by the time we'd got it, but when it arrived, my goodness, it came on a pallet. We don't receive a lot of things on pallets at the Maths Institute, so that was quite a surprise for reception. And then it turned out to be for the outreach team. Like, why are they getting pallet loads of stuff? Also, it's not a pallet load of stuff, it's a pallet load of one thing, an enormous cube made of squashy foam. So that was pretty bad. And Me Machine Rex wants to tell me, ooh, a Riemann sphere. A Riemann sphere's diameter is radius, and then rotated it around the origin to make a new sphere, which is infinity everywhere, called the infinity sphere. Good technology, love it. Right, is 4x squared minus y squared equivalent to another form where they're all divisible by d? Answer no, because 4x squared minus y squared takes the value minus 1, and the things it's equivalent to are the thing they will have to take the value minus 1 somewhere. So it can't be the case that d divides all of the coefficients of that thing that it's equivalent to, otherwise d would have to divide all the values, middle line, and therefore it would have to divide minus 1 over there somewhere. So we have this problem we have, which is like genuine quadratic form that's not equivalent to anything of this nice simple shape where it divides things. Yeah, so it genuinely has a problematic value that I wasn't expecting. I guess I've shown that you can't go from the first step to the second step. So you definitely can't go to the third step, otherwise you will be able to go back again or something, even if you throw in a kind of is equivalent to in the mix somewhere. I don't know. Yes. Yeah, each piece is like a chair. Have you been in the office? What is this? Have you been in the office? What's going on? Mary is now commenting on an object that is in my office, and whether it's squashy or not, or whether it's more like a chair. What is this? Moved it to a different office anyway, so you can't find it anymore. It's hidden away somewhere else now. It's gone into a better sort of storage place than literally right behind me at all times. It was under my desk for a while. I tried using it as a kind of uncomfortable foot support under my desk. It's, big squashy thing. Did I tell you the story with the Soma cube? Why we've got a big extra piece? maybe not. It's about chiral symmetry. I must have done the chiral symmetry story, right? About the Maths Festival and the Soma Cube. I'd love to do the chiral symmetry story if I haven't already done that. No. Okay. We'll try and get Soma Cube up on Wikipedia. Story time. Here's a Soma Cube. It's sort of a dissection. Right, okay. It's a puzzle where you try and put the pieces together, which sometimes people call a dissection puzzle, but occasionally people say, well, no, not a dissection puzzle, because it was invented genuinely as a putting it together. The person didn't start with a cube, dissect it, and then challenge you to put it back together. The person started with the pieces and asks you to put them together. We've got a massive one of these for the Maths Festival. We bought it this year from people who make massive, squashy, soft play pieces. We're very happy with it. The day before the Maths Festival, or maybe 2 days before the Maths Festival, I unpacked it again, having marvelled at its size and worried about how it was going to interact with small children. Unpacked it again to have another look and realised that, well, do you see here it says there's this pink piece and this yellow piece, or down here they're described as A and B, and they're chiral, which means that they're sort of mirror images of each other, like your hands are chiral if you have two hands and they're not both left hands. Anyway, if you have hands like mine, they're chiral in the sense that they're mirror images of each other, sort of. These pieces are mirror images of each other. And I realised when I unpacked it one last time to give it a bit of a clean at the last minute, I realised that they'd given us 2 matching pieces. And it was kind of amazing that even with 2 matching pieces, so imagine you have 2 of these yellow ones over here and no pink piece. Even with that, so one of the pieces is backwards, or inside out if you prefer. Even with that, they'd been able to make it into a cube and send it in the post to us. So here the pieces are assembled into a cube, but we had not quite a Soma cube with one of the pieces the same as one of the others, and they'd still been able to make it into a cube. And then the challenge was, well, the challenge at the Maths Festival was, is anyone going to notice? Probably not. We also had some small Soma cubes, so people could spot the difference potentially. And the ambassadors on the day, so Oxford students, played a game where they tried to work out, could you build the same things? Not all of the same things, but could you build the same shapes with the pieces that we have? So there's people try and build a cube, but they also try and build this other stuff. We've got one of the pieces is mirror imaged. Not all of the pieces. Can you still build like a sofa? Can you still build, I don't know, this corner thing, or a dog, because they wanted to build a turtle at one point. Can you still build them with our not quite the same cube? And over the course of the entire day, they worked out that all of the things they cared about, they could build with the giant squashy, not chiral Soma cube. So that was really good. And then after the Maths Festival, I ordered a replacement part. I sent them an email to explain that I wanted a custom piece that was like the one they'd sent us, but the other way round. Which was quite hard to describe in an email. If you want a maths writing challenge, you might like to explain. I mean, I cheated by linking to the Wikipedia page, but if you want a maths writing challenge, you might want to think about how you would explain that you've been sent 2 of these and none of those. And it's very important to you that the replacement piece they send is not a third of these. That would be quite bad. How do you write that email? What maths words do you use to try and communicate that I would like a mirror image of the thing? Oh gosh. So like an L, like a small L, but with a top piece on it, but on the right. Oh gosh, with the L facing. Oh dear, with it facing towards you. Here are the coordinates for where I'd like all the corners. Oh gosh. Yeah. So communication challenge. So I know we have a spare piece, and because our Soma cube is now fully, has a chiral pair, one of each sort. It matches all of the small Soma cubes we've got. We're very happy with our Soma cube, but we have a spare leftover piece, one of the bonus pieces that we had, which It currently lives in my office or in storage or just around. We haven't quite worked out what to do with it. But yeah, it's squashy. It's like a chair. Just go for it. Yeah. So I've got this extra. I've got 1/7 of a Soma cube extra, but it's from a mirror universe. If I ever get to the mirror universe, I might find someone who's had exactly the opposite experience, and I guess we could swap. Too late now because I've got a replacement, but I need the piece I've got belongs in a mirror image Soma cube. That's a silly thing to say because the Soma cube includes both, so it is its own mirror image. But I need to find someone else. No, because someone else might have the same. Yeah. It's like getting 2 left shoes in the post. You have to be like, right, okay, I needed to build me one. Like that. Exactly like that, really, but different. Please, sir, can I have a flipped thingy of the thingy yellow piece here in this picture, as I need it to be cool? Yeah. Good email. Yeah. So I became a tiny bit worried that possibly the squashy people, because they can build it into a cube, they might not have noticed. So they might make all of them like this. It's probably easier to make 2 pieces the same than to make mirror images. And then they do fit together to make a cube. And we think most of these shapes you can still build, so you can still use it as a semi-cube. All of this theory still holds, so you can still solve it the same. The logic for solving it is still pretty similar, which I like. If you would like a semi-cube, they sell little wooden ones and also massive squashy foam ones. But maybe explain about chirality if you're ordering them custom made. That's the moral of the story. Right, good. I don't think it's emotional damage. We had a budget for equipment, and it's quite hard to spend an equipment budget in a maths department at the best of times. And this was a good way of spending the equipment budget. Right, okay, that was story time. I am very upset. That's not a direct quote, is it? What was I upset about? Was it the numbers? It's probably the numbers. Good. Okay. So back into 6.14. I've got to read half a page before 5 o'clock, haven't I? I've got to try. Page 185. Here we are. Okay. A form of discriminant delta. We're going to see that if it represents a power p to the k for a prime not dividing the conductor of delta, then it's primitive. And we've got to be really careful with what conductor means. So here we go. If a form q representing p to the k is not primitive, it's a multiple of another form by some integer d, which might or might not be the conductor. This number d divides every number represented by q. So we're going from the kind of bottom line of my 3 cases to the middle line. Divides every number. In particular, it divides p to the k. You can't divide p to the k unless d is a multiple of. I would say d has to be a power of p, right? Yeah. Okay, never mind. So it's d divides the conductor. This means that p divides the conductor. Okay, we only needed quite a weak result in the end anyway. Why does it divide the conductor? Oh, right, sorry. If you can go from the second line to the first line, since d divides the conductor. Yeah. Okay. Good. Because d divides every number represented by. No. Yeah. Okay. So we're going for not primitive. Therefore, it divides every number, so it divides the conductor. Because you could just pull out that factor like we did in the margin. So prime divides the conductor as well. Yep, okay. So if p didn't divide the conductor at all, then q must have been primitive. I don't like it, in the sense that I agree that it's easy, but I'm going to really struggle to hold it in my head. Oh, I don't know, maths do. That's a great example of it's gone from chat, but great example of a clever question. But I feel like maybe does the conductor have anything to do with the field generated by the roots of the form? Jesus help. I know nothing about the fields generated by the roots of the form. I can't stress that enough. Right, okay. It could do, because I know nothing. I've struggled to know anything about the conductor, and then does it have anything to do with the root, the field generated by the roots of the form? Like, I mean, I guess the answer just no, because the roots of the form is potentially different for each form that has the same discriminant, whereas the conductor is a property of the discriminant. Are they just? I don't know. Not knowing is fun. Right, okay. Primes dividing the conductor seem to be the problematic ones. Here we go. On the next page, we've got a big table. Well, let's have a look at the big table before the break. All the equivalence classes of forms, both primitive and non-primitive, for non-fundamental negative discriminants up to -99, along with the prime powers represented by these forms for primes p dividing the conductor. Oh my goodness. Which prime powers can you do? Isn't that theorem 6.11? Maybe not. And we're going to use square brackets for quadratic forms. If non-primitive forms of a given discriminant represent all powers with k greater than 1, then primitive forms of that discriminant represent all powers with k greater than or equal to 3. Oh my goodness. This statement is optimal for some discriminants, but not for others. I think we're going to have a look at the table. In the table, one can see that primitive forms represent powers of primes dividing the conductor, but not these primes themselves. As we will show in 6.15, as we will show, underline it when you see it, a prime can only be represented by a single equivalence class of forms of a given discriminant. The phrases are just getting too long for me. A single equivalence class of forms. What does that even mean? Help. Forms are equivalent if you can transform it, if they're the same values, if they have a node in common and you grow from there. Equivalent if you do some transform. So the equivalence class is then that's not everything with the same discriminant. It sometimes is, but not always. Is it called the class number? There are several sorts of class number though. Gosh, depending on what sorts of equivalence we were talking about, we sometimes included reflections and sometimes not. Some of them are symmetric and some of them are not. There's a separate number for that. Some sort of class number. I'll remember it at some point. Non-primitive of a covariant discriminant and a prime p dividing the conductor for discriminant delta is represented by p times the principal form of p squared. So p is represented by a non-primitive form and hence cannot also be represented by a primitive form. What on earth is going on? The uniqueness of forms representing primes holds also for powers of primes that divide the conductor. The table may not hold for primes that do not divide the conductor, even if we restrict. So we saw some examples at the start of this chapter about whether or not primes, we sometimes saw them come up in multiple places. Is that what we're talking about here? We now have a table that's showing us the same thing. Let's look at the table. Infinitely many different powers of PK. But infinitely, oh gosh, represented by different primitive forms of fun. Just put drawing double plus, but in the other cases, one must use general theory. Like first case, this one, next case, -60. Things are not feeling very chill. The method's in the next section. I sort of think this is telling me what's coming up rather than telling me anything I'm supposed to understand, right? Prime can only be represented by a single equivalent class forms of a given discriminant. A prime p dividing the conductor for discriminant delta is represented by p times the principal form of the discriminant. No, gone. A prime p dividing the conductor for discriminant delta is represented by p times the principal form of discriminant delta over p squared. So hang on, right, this is saying if I think I can almost see it as a sentence. A prime p dividing the conductor for discriminant delta. So then this over p squared would still be a discriminant. So good news. and the principal form of that discriminant would represent tea time. It would represent tea time. And there's also a comma. There's more of this sentence coming after the break. A sentence so long that we may run ads in the middle of it. I'm P dividing the... I'm really struggling with the English language comprehension stuff here today. I don't know why. My brain's just not in the right place, I guess. P dividing the discriminant is represented by P times. Prime P times the principal form. What is the principal form of discriminant that? Depends, doesn't it? Whether this is 1 or 0 mod 4. You put that in front of the y squared, don't you? And you put 1 out the front, and then you put either 1 or 0 in the middle, and you get... You have to divide by 4, sort of, maybe. P. So if you multiply by P, then it'd be represented... I sort of want to know about principal forms again. I sort of know what that means, but I feel like I just tried to say it and I screwed it up. So we're going to have another go. But I think crucially that takes the value 1 somewhere. So multiplying by P is a way of getting the prime P. So then P is represented by non-primitive form because we just multiplied some particular thing by P, and hence cannot also be represented by primitive form because we're going to show that it can only be represented by a single equivalence class of forms, and primitive things are not. Primitive things are not equivalents to non-primitive things. Something that would have been helpful to remember earlier when Maths Teacher 2 asked me about the 4-1 case of being equivalent to something else, because primitive forms are never equivalent to non-primitive forms because non-primitive forms, all the values are a multiple of something, whereas in when a primitive form, that's not the case. Yeah, I'm not saying I've had enough of this one, but it does occasionally drive me up the wall. Right, okay, let's have a look at the big table and then take a tea break. See if this helps. So this is going to be a table of things starting from -12 and going down. It's going to tell us the conductor here, which is the largest square that you can divide this by and still get something left over that's 0 or 1 mod 4. So careful, 36 here. I know that 36 has larger square factors, like for example 36, but if you divide it by 36, you would get -1. -1 is 3 mod 4, that's not a discriminant, there's no quadratic form that has discriminant -1. So, what are these? Why are these so irregularly spaced? I thought they were everything that is 1 or 4, 1 or 0 mod 4. What is that? There's a Q prim. Is that an example of a primitive quadratic form that has that discriminant? And an example of a non-primitive one? Because you could have quite a lot of equivalence classes, couldn't you? Oh, well, never mind. We've got 2 examples. And P to the K is that the primes represented by that form? Well, tell me more about this table. All the equivalence classes of forms. All the equivalence classes. Oh, right, sorry. So there'll be multiple rows. Will there? Oh, multiple rows. If there are multiple primitive ones, and maybe there's multiple non-primitive ones, with these multiples out the front. And then we're looking at which powers of primes dividing the conductor you can make. If we got a non-trivial conductor like 6 somewhere down here, that would be an interesting one. No, because there would have to be 36 times 4 or -3 or something, which is too large. I think only just. I do love the little T-Rex. It's so cute. Why is it so cute? This dinosaur. Predator of the ancient past. Why is it so cute? Right, okay. So I'm going to read one more time what I'm looking at. All the equivalence classes of forms. I see now there's multiple rows. Both primitive and non-primitive, there's multiple columns. For non-fundamental, that's why we're skipping some of them. It's non-fundamental. Non-fundamental are ones, I think, with non-trivial conductor, so that we can look at the effect of conductors on things. Along with the prime powers represented by these forms of primes P dividing the conductor D to see that. So you'll see that it's really complicated. Primes dividing the conductor, prime powers, which ones can you make, which ones can you make. And so the table here says you can make 2 squared, which is 4, with this quadratic form. X squared plus 3y squared, you can, if you plug in 1, 1, get 4. You can't make any other powers of 2. You can't, for example, make 8. That's good to know, isn't it? Good fact. And this one you can make the number 2. Okay, so sometimes a prime power is represented twice. Sometimes the prime power is represented twice by primitive things. Sometimes it can't be both. So there's nothing on the left that's also on the right. Oh, why has this appeared twice? So this 8's appeared twice. I thought they said it could only be represented by a single equivalence class. Let's read back again. Just a little bit, back a little bit. Oh, was that just for a prime P? Represent powers of primes divided in terms but not these primes themselves. Never the prime themselves. Single equivalent class forms. So you can't, because P is represented by a non-primitive form. But we have non-primitive forms here. Oh, right, there's some. There they are. So these are some primes over here. 2 to the 1 is always on the right. 3 to the 1 is always on the right. Read the sentence again. Is the conductor the discriminant of a form? It must be the discriminant of some. It must be the discriminant of some form, because it's. Oh no. The conductor itself doesn't have to be anything, right? Is it the GCD of the discriminants of all equivalent forms? I don't think so. Equivalent forms have all got the same discriminant, so we're just blindly taking the GCD of all of the discriminants is going to give you the GCD of loads of repeated things. So it's not obvious to me how to get from minus 36, how to get. I think we did have a bit of maths about this at some point a few chapters ago. Oh, sorry, divided. Is it the discriminant of a form divided by the GCD of the discriminant of all equivalent forms? No, I think that's always 1. Yeah, I think that's always 1, sorry. Because all equivalent forms have got the same GCD. Yeah, sorry. One more on this, so I need to reread just one more time. The primitive forms represent powers of primes. The primitive forms represent powers of primes, but not these primes themselves. Yes, I see. They represent powers of primes, but not 2 to the 1. That's what that sentence means. It says there's always stuff over here, except in this case. So no, they don't mean that. There's sometimes stuff over here, but never stuff to the power of 1. That's always on the right hand side. What a tricky book. Oh, here we go. It's time for proposition 6.15. Is it time to do the thing? Is it time to do the thing that we said we would do? We will show very soon. Okay, so we've got a bit of maths coming up after the break. We're going to take a slightly belated tea break, just like the cricket does. We're going to see how the cricket's going, and we're going to come back and attack this with some prime maths. How bad's this proof? It's not always based on length of proof that makes something bad, but it's a long proof. Okay, that can be our target for today. Page and a half to understand this proof of proposition 6.15 about stuff. And then, it leads on naturally to another interesting fact from the same argument on the end of that page, which we might get to. Okay, but I think we're going to come back after a tea break here Yeah, I wonder about Maths222 in chat says they have stream lag, and I worry about bitrate. I turned down the bitrate. I don't think it's that low. It's probably not that. Right, good. Okay, I'm going to be back in a couple of minutes with a fresh cup of tea. You're welcome to grab a cup of tea or a glass of water, or just have a break from looking at screens for a couple of minutes. If you do glance over at this screen that you've got, then you might see that it's showing you some ads. You're welcome to ignore the ads if you would like. You won't miss anything because I'm going to go to a back soon screen and be on mute while my kettle is boiling. You don't need that. Bonus content, the sound of my kettle boiling. No. Right. I always worry that I'll come back and it will just be me and the maths. Actually, that'd probably be fine. Been there before, just me and the maths. Right, see you in a minute and a half or two. Tea time. Yes. Thank you, Mary, for redeeming tea. Right, what do I press? I press this and that and that. Welcome back. I don't know how many minutes that was. What's going on in chat? Genius move, says someone. Woo! Enjoying the tea break. Wait for this. Right, good. Welcome back, everyone. I think I've unmuted and everything. Right, what are we doing? We're reading 6.15. It's that part of the stream where it's towards the end. I'm a bit tired, but we've got to read a big chunk of maths. Here we go. Oh no, right, okay. Two non-equivalent forms of the same square root both represent the same number. Does not happen for representations of one or primes or powers of most primes. Presumably something about dividing the conductor, which we've seen before. It has been 87 years. Thank you, chat. Always, never hyperbolic in chat. I checked the cricket. The cricket is going to end in some sort of 5-day draw, and I checked the F1, and the F1 ended how I left it as well. So it's nice to know that although sport was happening while I wasn't looking, nothing has actually, like, you know, it's not like any of the cars overtook each other, and it's not like any of the cricket teams progressed towards winning a game of cricket or anything. So everything was in sort of sporting stasis. But like when you look away from a football match and no one scores while you're looking away, which is a curse that some people wish they had. Anyway, oh, you see, it's 87 years for you because you've been on some sort of speed of light trip and you've just got back from your speed of light trip. Wait, no, that would make it 87 years for me, but not for you. Yeah, you would experience time as normal and I would have aged 87 years. You need me to get in the rocket. Maybe that's where the kettle is. Yes. Oh dear. Oh, I'm sorry I've dragged you away from your family. Are you on holiday? Oh no, you're on holiday, aren't you? That sounds like you're on holiday. Hello, everyone on holiday. Well, I'm going to try harder then. Maths 222 is tuning in from, I think, in inference, yes, some sort of family holiday, and they're here with us learning about quadratic forms. So we should learn about some quadratic forms so that they've got something to report back to their family about. Here we go. Good news. We've worried a lot about whether forms can take particular values, and the last thing I want is for different forms to take the same value as each other. I would like to sort out all the values and say there's a simple rule, and these ones take these primes, those ones take those primes, and then work out other numbers by combining them together following this group theory sort of thing. That's what I'm hoping to read. Good news. They can't agree that they're both going to take the same prime. Even if they have, right, so if they have the same discriminant, you might worry that both represent the same prime, or both represent 1. Both representing 1 would be a bit weird. So same discriminant and both represent 1. Then, well, okay, then they're going to be equivalent forms. You're going to be able to deduce that all of their values are the same. There's maybe a corner that's the same, and from there you can grow out the rest of the binary tree to say, oh, yeah, they were just taking the same values everywhere. Those are actually equivalent quadratic forms, which is fine. We have these equivalence classes. They'd be in the same row of this table. Sure. Things in the same row, they've got the same values, so of course they can both take the prime. Let's point over here. They can both take the prime 3, that's allowed. But different ones can't. If you like, this goes, oh, this is pretty, isn't it? Over here, look. Do the 1, 2, 3, 4, 5, 6, 7, 8, and so on. They never overlap. Actually, it's just about primes. We're going to do prime powers later on. Here it is. The same conclusion holds when both represent the same power, p to the k of an odd prime p that does not divide the discriminant. Oh no, that was a case where it does divide the discriminant. Oh, never mind. Look. Don't think about the table right now. Right. The last statement is also true for p equals 2, but the proof is more difficult, so we're going to wait. Underline it when you see it. We will wait until the next chapter. Oh, there's always like foreshadowing for future maths. Can be form of the same discriminant can be found in the table on the previous page. Oh, right, okay. Powers of primes divided discriminant carried by non-equivalent forms of the same discriminant. There were examples in here. Example of that is, I pointed out the table as if it wasn't the case, but it is the case. Look, different forms, both taking the value 2 cubed. And this is the case where 2 is not odd. Can I find examples with 3? If it divides the discriminant, then maybe I can find examples where 3 is in both. Yeah, there's one. So 3. So it's not just 2 being a weird prime. Also 3 does this as well. Okay. Oh no, Mary could be at the beach just finding out what other people could be doing if I wasn't running chill maths on Twitch. And it seems to be family holidays and just generically the beach. There's some sort of like everyone's going to the beach. Right, what could I be doing? No beaches around here. Sad times. Right, okay, here we go. We're going in. I've got a really no. I've made this mistake before. I'm intervening. I've got to really understand what it says before I try and understand the proof of why it's true. Okay, so there are two forms of the same discriminant. I think I've got a good grip on that. Both represent the same prime p, or both represent 1. Then they're equivalent. And then we'll do prime powers later. I hope it goes in that order. If it goes in the other order, then the second half is going to be really quick. K equals 1 included, or something. Right, okay. Good. Okay, suppose that Q is a form representing a number p that's either 1 or a prime. Feels weird to have bundled 1 in. Don't like it. Making me think things about whether 1 should count as a prime number. Don't love this phrase. Anyway, never mind. Good news, gang. P is sometimes 1 in this proof. The tuple graph has a region labeled P because it takes the values. That's what the tuple graph does. And we have seen that the H labels on the edges, it has been approximately a month since we thought about any H labels, but here we are on the edges adjacent to this P region. We have seen that we saw this so long ago, form an arithmetic progression. We have this arithmetic progression rule, I think, with increment 2p, when these edges are all oriented in the same direction. So if you read around the P region, then you get arithmetic progressions going on. 2p? 2p is a bit of a surprise. And that's the increment in the labels though. So the thing that's going on here is that we have p and then x. Let's label x here and y here. So then the next thing is you go from x to p plus y to p plus 2y minus x. To keep the arithmetic progression going, x to p plus y to another increase of p plus y minus x gets you to 2p, I suppose, actually. 2p arithmetic progression? Yeah, arithmetic progression. So then, reading off to the next one, the arithmetic progression previously. No, I'm not going to get 2p off this argument, am I? With increment, I am going to get that, because this increment is p plus y minus x, for like the increment, and then the next increment is going to be 3p plus 2y minus x minus y. 3p plus y minus x, which is the same thing but increased by 2p. So that's a mess, but I kind of vaguely believe this is just the arithmetic progression rule that we've had for these tuple graphs, so we're all good. Right, good. Okay. With the discriminant formula like this, where h is labelled on one of these edges. I preferred the one that was this b squared minus 4ac, but it all boils down to the same thing anyway. Q is the value of Q for the region on the other side, because you look equivalently somewhere else, and then it's not amazing, but you get these like the values a and c would be the values on the left and right. So discriminant being equivalent, discriminant being conserved by these transformations that we do. I prefer to think of this as b squared minus 4ac, kind of the same idea. Anyway, never mind. Not quite b. B minus a minus c or something. That's all good. Whatever. Determines Q in terms of these things. This implies that delta and the arithmetic progression determine the form Q up to equivalence. Ooh. Wasn't paying attention. This P is non-zero, the equation like this determines Q in terms of delta and H. This implies that delta and the arithmetic progression that you've got determine the form Q up to equivalence. Since the progression determines P, and any H value in the progression then determines the Q value corresponding to this H value, so Q is equivalent to that one. So this is saying that a form that takes the value P is determined by the determinant. Of course, we're very interested in what the discriminant is. Very interested in the discriminant, and we're also interested in the value, the arithmetic progression that you see around that region. That's enough. With a minus? I don't know. So Q is equivalent to this. In the case P equals 1, now I'm going to split out the case P equals 1. Q is equivalent to this. yeah, if you show me delta and p and h, then I can work out everything. So I'm good. I'll write down this one is equivalent to this. In the case p equals 1, the increment in the arithmetic progressions is 2, so there are two possibilities, even and odd numbers. We know that h has the same parity as delta because of this formula, I think. If h is even, then so is delta, and if h is odd, then so is delta. So delta determines which of the two progressions we have. Actually, only one of them is possible. As we saw in the preceding paragraph, this applies to forms determined by delta up to equivalence. So that's good, right? That means we're done. If you're talking about the case p equals 1, then and you've also fixed the discriminant that you're talking about, then that says, well, you've got a region 1 where it represents that number 1, and then you look nearby. Is it doing odd numbers or even numbers nearby? If the increment is 2. Is the conductor? No, I share a barber with the Lego people. Lego hair is an important it makes my life much easier. I get up in the morning, I have a big row of human-sized Lego hair, and I just clip the hair on, and then that's my hair. I could, I suppose, get other Lego hair because they make different sorts now, but I'm sticking with the classic Lego hair. That's how I do my hair. So for the barber, I just go and I can get a replacement piece if I need, but stuff's pretty durable, being made of ABS. It's also the look favoured by Sheldon Cooper. Thank you. Math222 is asking me tricky things about the conductor. I think they're hoping that I read their chat comment and say yes, that's exactly what the conductor is. But I only understand the conductor as the largest square that you can remove from a number, such that the remaining number is 0, 1 mod 4. So all of their questions are actually quite hard for me. Divide by the GCD of A must be minus C for 3 adjacent cells of the top. I don't even think. No. The case 4x squared minus y squared, it kills a lot of this, because 4x squared minus y squared has got this awful -1 region. So all your GCD stuff, oh god, but you want me to look at A plus B minus C. So I need to think about what's going on nearby. Oh, you've looked at exactly that one in chat. Oh dear. For 3 adjacent cells. What can I do for this? It feels like it would be equivalent A plus B minus C. What do I think about A plus B minus C? I feel like A plus B minus C is the H value on this edge. It's the thing about arithmetic progressions. So H val is A plus B minus C. So I think what they've noticed is we actually know that delta is H squared minus 4PQ for which here is A and B in their kind of notation. A's and B's. I think the conductor is 4. So I sort of don't know where to go from here. Right, okay. Pattern spotting. I have a chord. Oh no. Maybe I shouldn't read chat. I'm in G major. This is good to know. My weird mumbling is in G major. I'm taking that to my grave. That's brilliant. Right, good. Okay. So I was happy with this because it felt like maybe there are two different forms that might both take the value 1 and have the same discriminant and have different arithmetic progressions around the outside, but thinking about the equation delta equals and then something to do with h squared. The parity argument kills that. I'm excited to see what they do for the case that p is prime, because there'll be loads of cases. And h squared, oh no. You're going to tell me if the prime doesn't divide. Which case are we in? It'll be about primes dividing delta, right? Let's look down. Let's just read it. Let's just do it. I didn't even stick the G major chord. I thought I could just go for it and no one would notice that I don't have perfect pitch. Oh no! Okay, let Q1 and Q2 be two forms of the same discriminant, both representing P. For Q1, choose an edge in its total graph adjacent to P region. Good. H level H1 and Q level Q1. So what's opposite and what's the term in the arithmetic progression? Q2, go for it, do the same thing. They have the same parity. That doesn't feel like enough anymore though for the actual h values. We know that the h values form an arithmetic progression with common difference 2p, but they could be anything modulo, there are 2p, many arithmetic progressions. I guess probably the one with everything factors of p doesn't count, so there are 2p minus 1 options, so I'm a bit worried. Same parity as delta, fine. Delta is like this and like that, and hence, this has gone very number theory very suddenly. Oh, look. Alright, quite good actually. h1 squared is going to be h2 squared mod 4p. Oh, that's really good. The squares agree. The squares of these things agree. And mod p, you can solve quadratic equations like that. Mod p, off you go. h1 squared is h2 squared. So devise the difference of two squares, factorise and solve. P is prime, so devise one of these two factors. All of this is just saying that you can do square roots modulo p. I'm going to ignore the 4. So h1 is plus or minus h2. I'm worried that h1 might be minus h2. I'd love them to be equal, because if the h values are equivalent, if the h values are the same, then given delta and given p, I think actually the q values are the same, so then we're talking about the same, we have value, opposite value, and the h value in between gives us the same quadratic form in both cases. So I've got to eliminate this h1 is minus h2. Oh, just change the orientations. Is that allowed? Depends if we're counting equivalence including reflections, right? Or just does it? Yeah, I think it does. Maybe? Maybe not. Hang on. If we are counting reflections as equivalent, then I don't care about any of this direction stuff. If we're not counting directions as equivalent, then yeah, sure, there'll be two. There'll be this one and its reflection, so the statement is not really true anymore. So we have to count reflections as equivalent for this. Good. Bit of a win. Someone in chat, it's me, Machine Rex in chat, says James in Minecraft is beaming SOS signals hard right now. What? Oh, my huge house. What is this? Oh, yeah. Hang on. There is actually a longer Minecraft conversation I haven't been keeping up with about my terrible Minecraft setup. Ha! Good. Right. This is quite good. I thought we were now done because we'd have the same h1 value. Actually, we need to get up to 2p. And here's the parity fact. It's come back. So h1 minus h2. If they agree mod 2 and they agree mod p, Chinese remainder theorem, they agree mod 2p. Because the solution to x equals h1 mod p and h equals 1 mod 2 would be, combine them together with the Chinese remainder theorem. It came back, Chinese remainder theorem every time. They're spelling it out here with the divisibility, but I think you could just see out here. Amazing. Love to see it. The arithmetic progression. Okay, here's the punchline. The arithmetic progression of h values suggesting that the p region for Q1 is the same for Q2, since 2p is the increment for both progressions. They've just been, they're out perhaps by a bit. This implies, because you now have same region, and via the discriminant fact you have the same opposite region. Once you know the thing between, we're good. When p equals 2, you've got a slightly different argument, because, as always for the prime 2, you're going to need to do this. The arithmetic progression rule is also known as Conway's arithmetic progression rule. Why is that not in the book? It's a good fact. Here we go, mod 4p. We can still do that mod 4p. The parity thing is not the same anymore, right? Down here. Oh no, the parity thing is still true. It's just not good enough, and we can't combine them together at the end. So when p equals 2, this becomes... Oh no, we can't remove the 4 at that point. We have these squares are equal mod 4p, and that is mod 8. But actually all odd squares are equal mod 8, so this doesn't help very much. Since 2p is 4, okay, the 4 possible arithmetic progression h values are not 1, 2, or 3. We can interchange the possibilities of 1 and 3 just by reorienting the edges. Okay. Yeah, fine, okay. Minus signs. Leaving only the possibilities h is 0, 1, or 2 mod 4. These are distinguished from each other by congruence. Since this thing squares... Oh, you've only got one odd case now. If you count plus and minus signs the same, then there's only one odd number mod 4. Only one square for that. Right, okay. 4k plus 2 squares to 4 mod 8. So this is telling us that you can do these square roots, but the thing we really need is to get h1 squared equals h2 squared to mean that h1 is equal to h2. This thing that catches people out so much. That if x squared equals y squared, then x equals y, and it's just sort of not true. We would like that to be true, and you can always get away with it, especially if you're blind to plus or minus signs because of a reflection property. You count those to be equivalent. For some reason, the minus sign doesn't affect the topograph of the quadratic form; just reflects it. So that might be one reason why you could get away with this. And then in the mod p world, well, you might have extra solutions. The mod 8 world doesn't let you do that at all, but you can get away with it apparently by being really careful. Right, John Conway, the internet. I should have guessed. It's cool. Must be John Conway. Okay. Right. Finally, here we go. Finally, what is this? Q1 and Q2 both represent. Oh, we've got to do prime powers. Prime powers. Prime powers. I haven't done prime powers yet. Line of proof above. Everything checks out apparently. P to the k divides this difference. We're trying to solve h1 squared equals h2 squared mod p to the k, and that's the same. If p to the k divides either factor, then we're done. If p to the k does not divide either factor, then both factors are divisible by p. Hence, p divides their sum to h1. Oh, that's a problem, right? Since p is odd, this implies that p divides h1. And so p divides this. Thus, if p does not divide delta, then the case of the p to the k divides neither of those. Okay, so for primes not dividing the discriminant, this doesn't come up. So you're fine. So this bonus fact at the end was about odd primes that don't divide the discriminant, and that's so that we can play the same games about solving things at the end. Right. I quite like this idea about solving x squared equals y squared modulo some other stuff. Modulo 4p, but 4p to the k, but don't worry too much. Like, if something goes wrong, then go back and look at the discriminant and say, probably the prime divided the discriminant in that case as well. So don't worry about those. Okay, good stuff. for quadratic forms with discriminant 100, there's only one way to make 27. If any. Do I have to say if any? Don't know if I do. Right. Some creative writing happening in chat. Off they go. Okay. Yeah, I think we proved earlier, didn't we, that you can always represent a prime by some form, and now I think we know it's at most one. Let's look at this other interesting fact, just to finish up the page. Same label n, where n is either 1, a prime, or a power of an odd prime. We worried about this case a lot before. We were worried about these regions with 2 zeros or regions with 2 1s and what was going on around them. Apparently you're supposed to go and look at the discriminants and write down the facts over there and solve some quadratics modulo primes or something, which is fun. Two regions with the same label, power and odd prime not defined discriminant, then there is a symmetry of the topograph that takes one region labelled n to the other. Because it's equivalent, I think. Similarly for positive discriminants and for the same numbers n, yeah, I mean, we'll sort of try to take it to the other one. There's a symmetry that switches the ends and you might need to reflect, but there's a symmetry that switches it, interchanges the two ends, and then the proof is going to say it's equivalent, so you must have the same. No, wait. How's this proof going to work? Let's read it. For the same numbers n, if there's one region labelled n and another labelled minus n, then there is a skew symmetry taking one region to the other. What was the skew symmetry? Was it where you also multiply by minus 1? Go to minus q. Okay, suppose first there are two regions having the same label n. So in the proof and the previous proposition, each of those is adjacent to the edge of the same label h, and hence the labels q across those are all the same. And then you find from there. So take one and take that edge to the other one, and they're the same. So everything grows from there. The other case is that one region is labelled n and the other is minus n, q and it's negative. Then each have a region labelled n, so there's an equivalence between those, and then flip back it again. That's q region. Okay, nice. Every time I look at chat, it's just terrible. You can sort of understand the conductor as just a fact about the number. It doesn't have to be anything to do with quadratic forms in a way. So I'm sort of suspicious that the right way to solve. Yeah, let's go and let's do that next. Oh, we're almost at the end of this mini section. Let's read this half page, and then if we've got 10 minutes, we'll go and think more about conductors and what they are. Yeah, okay, fine. It's about infinitely many primes. It looks really cool. Here we go. For each discriminant delta, the set of primes represented in discriminant delta is infinite. Oh yes, I was worried about, can you make all the primes? It might not be, but at least it's infinite. Okay, in each discriminant delta, there's a form like this, representing 1. I love these ones. B squared minus 4c. Yeah, that's always the case. You can make B be 0 or 1, depending on whether you want something that's 1 or 0 mod 4, and then C is supposed to be the quotient of 4 in the expression. Determinant is 4 times what? Plus or maybe not 1. Not my greatest sentence that I've ever said out loud. We can assume C is non-zero since the top graph of Q will always be at least one region adjacent to the one region that is not labelled by 0. Otherwise, yeah, parabolic regions can have a 0 region and then most 2 0 regions. I don't like those ones. Let this be a finite list of primes. We allow repetitions. Oh, okay. We allow repetitions. Okay. So a really long list of primes with some repeats if you have to, if there's only a few things on your list. Let P be the product and consider the number Q of one big P like this. This is represented by Q since 1P is a primitive pair. That's where it's obviously represented by plugging in 1 and P. That's how you made it. If k is large enough, then we will have this is going to be greater than 1. Even if you're using negative numbers, that's all good. The size of it is going to be... I mean, what? This is weird. Okay. Much larger than 1 plus BP. Yeah, good. Okay. Oh, right. Do they mean mod n greater than 1? Almost all numbers have mod n greater than 1. Like, it would be really weird if this expression was always exactly 1 minus 1 or 0. How should I mean that? Anyway, never mind. Any prime p dividing n will also be represented by some form of discriminant delta. Because we've had this, any factor of, if you represent a number, then you represent its factors. We have this thing, if you represent a number, then you can transform and get n as one of the coefficients, and then if that splits into prime factors, you can do some shuffling around to write down something else that has the same discriminants at the start of this section, I think. We can go back and look at it when we go back and find conductors. This p must be different from any of the primes pi on the initial list, since dividing pi, and it's represented into this gives a remainder of 1, whereas p divides n evenly. Yeah. Thus we have shown that for any finite list of primes, there is another prime not on the list that is represented. So the set of primes represented. If you try and list the primes represented by discriminant delta, then do this trick where you multiply them all together and plug it all through. Definitely a B here. Definitely a B here. Definition of n from up here. Good. Right. Good. Hence the set of primes represented in discriminant delta must be nice. I got a bit lost in the middle. What was going on here? This bit felt really unnecessary. Why do you need to say that it's larger than 1? Oh, so that it's got some prime factors? You sort of need to generate something interesting, don't you? So these are the numbers that have interesting factors. Almost all of them. But we need to make sure this isn't just 1, minus 1, or 0. Which I suppose it's slightly awkward to talk about cases where this is 1. Doesn't look like it could be 1. P's not 0. B plus CP. I guess that could be 0 if we get unlucky. But not very likely. Good. Okay. Make this large enough. Yeah, you might have to write down the same prime. If you think your quadratic form only represents the prime 5, then you might have to write down lots of 5s. And you'll be happy, I hope, to put in this large power of 5 in here and agree that that's a number that's represented. That must have some prime factorization, and then you represent the prime factors of that. And if you put in enough 5s, then this becomes super large. Has non-trivial factors, none of which are 5. So then you're guaranteed to get some new prime. Okay, good. Right, standard. Okay, right. I think we're clanking to the end of section 6.2. Yeah. Ooh, this is a good section, actually. Is this the section where we're still in the section where we learned about Legendre symbols? Go away, tiny fly. Oh my goodness, loads of exercises to skip. Let's go. Oh, that is good. Except for in 2 special cases. Show that if this represents 2 together, I've been nerd sniped by an exercise with n odd and k greater than 0, then n is 7, not 8. N odd and k greater than 0. This is what we came for, isn't it? Big power of 2 up here. Then n is 7 mod 8. So is this going to be boring then? So is this just thinking about squares mod 8? Maybe? Maybe. So mod 8. I could do some even odd stuff, I suppose. But the thing I'm thinking of is if x is odd, X is odd. There's 1 mod 8. This very much looks like it might be 0 mod 8. So n would have to be minus 1 mod 8 for this would. If x and y are both odd, fine. If x and y are both odd, then it's kind of obvious, unless k is quite small. Which might be this case for small k. I should think about small k separately. If one of them is even, then we have a problem because we're trying to make a big even number. Again, think about small k separately or something. Okay, it's bigger than 0. We're trying to make an even number, so one of them is odd and one of them is even. They've told us n is odd, so mod 2, we have a problem. And if both of them are even, then I kind of want to divide both sides. And again, I'll worry about small values of k, but large values of k I can divide both sides by 4 and carry on this argument. Carry on dividing by 2? That feels a bit sketchy though. Yeah, I guess I can run into a problem where both of these are even and this is a small power of 2, so I can't divide both sides by 4, but I should think about small powers of k separately. Okay, I think even, odd and mod 8. Mod 8 kills that. Good, right, okay, is this going to be next up? It's 6.3, genus and characters. There's some good stuff. Let's tag this bookmark. What I want to do for 8 minutes at the end here is a kind of special maths 2 thing, where we go back and learn what conductor really is, because we were getting quite close. So we're going to go back. I don't know how far back we have to go, but I'm going to try and find the definition of conductor. So that's safely bookmarked. Oh, I got through several pages today, didn't we, by skipping exercises. And I think if we just get through, what was this? 1, 2, 3, 191, 4, 5, 191. And some of this looks quite good. Representations by quadratic forms. We get through to this proof of quadratic reciprocity, which is down here somewhere. No, genus, still genus. Section 6.3 is not that long. And then section 6.4 down here is the proof of quadratic reciprocity that we already looked at. And then I think that's the end of section 6. I think. Oh, we read this and it was actually quite good. I want to read it again at some point because I find this tricky to hold in my head. Because then we can go and read about the class group and then we're kind of almost there really. So where was this then? Famous little theorem, Wilson's theorem, good stuff. So 205. You know, it's not a million miles away. It's about 10 pages of this. What was the factorization of a squared plus b squared plus c squared minus 2ab minus 2ac minus 2bc? We did that before, didn't we? We've definitely seen that before. Is it is this a trap? This feels like a trap. There's a minus sign in the middle. We've definitely had that at some point in a margin. That's been relevant before. Where have we seen that? We go back. Yep, Rex and Mary say that I shouldn't think about this. Yeah, the formula for discriminant using 3 adjacent squares. Let's go and find that. I don't know how we're going to find it, but because I can't search my notes for things I've written for like, does it look like? I can't really search for the word discriminant either. So I'm just going to do this until I see something that reminds me of that. Ooh, no, before this. There was something like this. They had some formula that involved. Oh, they broke symmetry, didn't they? Ooh, got half an idea. Going to explore half an idea. They broke symmetry. It was like a plus b minus c, which is their h. Because the thing you were thinking about before is like h. And that gives them a squared plus b squared plus c squared minus, or is it plus 2ab minus 2ac minus 2bc. And then you want to subtract 4ab off that. So kind of not quite a factorization. But if you've got something with a minus sign in, then I think somebody else might have been describing this as, in quadratic form science words, as being a pair of values a and b, and then they would call this h value for the difference between a plus b minus c, for that kind of jump in the arithmetic progression. So I think we're going to find this as h squared minus 4ab for an expression for, oh gosh, what is this expression for then? I think it's an expression for the discriminant, keep getting it wrong, because if you transform to a point where, if you transform to, sorry, draw the same picture again, if you transform, then you get this, where the kind of quadratic form is this. This term here is c minus a minus b, I think, xy. It's the thing you get when you plug in 1, 1. You get c minus a minus b plus a plus b, so it cancels out and you get this c. So I've transformed this to be kind of like the middle bit of the Ferrier diagram. There's a b, c when you plug in 1, 1 up here. So then this thing that you've written down is the discriminant, which I think they're going to say is h squared minus 4ab if I find my note. Can that be used to say something about the conductor? I don't know. Should we go and find the thing about conductor? My plan for this is I'm going to go back to, don't panic, but I'm going to go look at the title slide, and I'm going to use Phidon document. Oh no, not that one. Oh, that's nice, isn't it? There's this lovely front cover. Oh, some idiot has drawn all over my book. Who's done that? I've drawn some sort of binary tree on top on the front. Who draws on the front of a book? Ah. I cleaned it? Not quite. Lovely, pretty front cover. Okay. Not quite. Okay. Welcome back to Twitch. How do I do this then? Is it there? Is it here? Is it here? Search. I would like to know the very first time that we saw the word conductor in this textbook. Oh my goodness. Search. Well, let's see if it finds any conductors. Conductor facts. We've got a lag. We got 3 results. Here we are. Good. This is the page I wanted. Oh, look, it's counting how many times conductor comes up in this document. You see the count at the bottom. And the count, 54 matches. And 3 of them are on screen, so it can't be that important. Here's the page I wanted. We found out about conductor down here. Let's read this again, because it's turned out to be very, very important. Special interest in the discriminants for which all forms are primitive. All forms are primitive. So non-trivial conductor is going to, I think, mean not. It's going to mean there exists a form. There exists a form with d divides a, d divides b, divides c. D takes all the values, and thus the ones that you could write as 2 square bracket 1 1 or something like that. These are called fundamental discriminants. It's not a square times a smaller discriminant. For example, 8 is a fundamental discriminant, even though it's divisible by a square. 36 we saw is not really relevant that you divide by minus 36. We saw it's not really relevant that you divide by 36 because minus 1's not a discriminant. 2's not a discriminant of any form. Not congruent to 0 or 1 1 4. That's what you've got to do. Don't care about 1. Good. Fundamental discriminants are never squares. So fundamental discriminants appear only for elliptic and hyperbolic forms. Good. With 1 excluded, easy to check that the fundamental discriminants like this are these. Not hard to give a precise characteristic of the discriminants delta that are fundamental. First we write this. Hey, it's Penn Center. Hello, good to see you. You have to go and water the garden. Bye. Good. Only getting chat's doing great today. Right, if any odd square divides n, we can factor this out and still get a discriminant. And this is going to be part of the conductor. So this is to answer the question, what's a conductor? Still get discriminants since odd squares are equivalent to 1 mod 4. So multiplying that odd squares are not affected by the number is 0 or 1 mod 4. Okay, odd squares, fine. They're 1 mod 4, divide, multiply, I don't care. Off you go. And you can't be 2 mod 4. Okay. If k is greater than or equal to 4, then you can start factoring out factors of 4 because you've still got enough k left over, enough power of 2 left over that you're still 0 mod 4 after doing that. Which is not obvious. Okay. Equal to 2 or 3, let's still discriminate. K was 3, we cannot factor out factor 4, since this will give the excluded case. K was 1, which is 2 mod 4. If k was 2, we factor out this, exactly when it is 1 mod 4. Right, you've got to be really careful if you've got something that is a multiple of 4 but kind of only just, then dividing it by 4, a square number, be careful. You could be left with 1 mod 4. So you're worrying a lot about which multiple of 4 it is. Is it only, well, with this restriction that k is 2, only half of them work. The 1 mod 4 variety, not the 3 mod 4 variety. If it were 2 or 0 mod 4, then you wouldn't be in the k equals 2 case, you'd be in the k equals 3 case at least. Finally, when k equals 0, we have, so no 2s, you just got to do odd number business. 1 mod 4 please to be a discriminant. Off you go. Other than these special ones, which I'll ignore for now, you could be an odd number, but you've got to be 1 mod 4. That's allowed. This is odd. And then you've got the case where you're 0 mod 4, kind of only just 0 mod 4. If you're just 0 mod 4, only just, then you need to make sure that, oh, that's weird, n's got to be 3 mod 4. Product of distinct. Oh, we was trying not to bring out odd squares either. Why do we want n to be 3 mod 4? That seems weird. Oh, because we're trying to be fundamental. We're trying to make sure that when you take out this factor of 4, you're left with something that is not. You've got to be 0 or 1, but we've got to make sure that when you take out these factors, that it breaks. So here there are no squares to take out. Here there is a square. Look, there's one. Odd squares. Don't even think about it. Even squares. Oh, just provided you're 3 mod 4. Yeah. And then for very, very 0 mod 4, I'm now very suspicious because if you're very odd, it's not very, I suppose very would be very high power of 2, at which point you can just take out a factor of 16. So this is going to be rather 0 mod 4. You have 3 2s in there, so you're playing with fire now. Any more 2s and I'll start taking out a factor of, well, 2 squared. I'll take out a factor of 4 and I'll still be left with something that's a multiple of 4. So this is as much 2 as you're allowed. So 8n with mod n being a product of distinct odd primes. Good. I'm a bit worried about these mod signs and the concept of negative numbers and modular arithmetic, but I think I'll be all right. 8n with n, a product of distinct odd primes. No restrictions now because taking out that factor 4 doesn't work. Did I do a French thing? I don't remember doing a French thing. Imagine it. Just sort of accidental French. Sorry about that. Sorry for the ads. I think I'm saying I don't think I'm purring. I think I do a noise. I'm going to err on the side of it's not weird. Right. Can I give a formulation involving 3 adjacent cells? Well, I mean, you won't like it, but for 3 adjacent cells, from that, you can calculate delta, and then you can look at these cases. It's not good, is it? I don't think you like that. That's not what you mean. Like, so if you take A, B, and C, then you can calculate delta from that information. It is A plus B minus C squared minus 4AB, or if you prefer, A squared plus B squared C squared minus twice AB, B, C, C, A summed, which I think you prefer. And then from that, you've got delta, and then it's got to be in one of these 3 cases. Do I know a fun way to be fundamental? You've asked about the conductor there, of course. I mean, if you're not in one of these cases, then it's because you have some square factor that could be removed to leave something as 1 mod 4. So kind of once you know 3 adjacent cells, you can work out delta At which point you've reduced it to this kind of like purely number theory question about like once you know the number delta, there's kind of a task, but not much mystery. Not much mystery anymore, right? It's my best shot. Take the 3 adjacent cells, work out delta, try dividing by squares. Being a discriminant just means being 0 or 1 mod 4, so... Lots of 2s. If it's got... Okay. I haven't read the conductor bit out yet. Let's read that. Every non-square discriminant can be factored uniquely like this. Yikes. Keep going. Just keep pulling out square factors. These are the cases where you can't pull out a square, so everything else you can. Keep going. It's getting smaller. Keep going. Keep pulling out squares until you get down to one of these cases. What do you mean it hasn't got there yet? Keep pulling out squares. Either you can pull out a square, in which case do that, or if you can't, then you're in one of these cases and you can now stop. It's getting smaller, so you're making progress. Careful with your algorithms. Make sure they terminate if you can. Fundamental discriminant. Good. You'll get to one of these stopping cases. D is greater than 1. Number D is called the conductor of delta. Fundamental discriminants are those whose conductor is 1. We're going to do deeper properties in later chapters. And the class number is always a multiple of that. And there's a not too complicated formula for what this multiple is. The determinant class number is larger than fundamental discriminants. Outside the scope of this book. Okay. I did see the chat messages, so somebody in chat wants a kind of Lego version with glasses, and great news, they've already made this product. You don't have to put the sticker on, or you can scar me somehow, but like that's pretty close, right? That's good enough. And it comes with 2 friends and Hagrid, 3 friends. Oh dear. The thing about having Lego hair, it's easy to have a Lego representation of yourself. Yeah, we'll sell that as merch. There you go. Right. I'm struggling to get a good definition of conductor that involves just topographs only. I think I agree with Math 2 that I would like a discriminant or a version of the conductor definition where you just look at. Ideally, I would just look at one form. I would put it into the Desmos thing, and I go, oh look, the conductor of this form is 4 or something. Well, because it's a property of the discriminant, so I'd have to say, aha, the discriminant is 36, and I notice that the conductor is 2 from mystical properties of this thing. But really not very obvious, because, I mean, if I put some of these things in, there's a table in there, if I go back to 191, can I get to 191? 186, that's good enough, that's the page I wanted. Okay, so your challenge is you have to find some relationship between, and this is just, you know, so we've got in some case multiple ones to look at, like the 225 case looks very different from the 109 case. In fact, they both take the value 3 squared, so if you look at both you might notice something going on. But to look at the 109 form and to say 3 from there, probably you've worked out the value minus 36, and then gone from there. What's D? It doesn't have to divide all of that. I mean, it also has this form. So if you're looking at this one, you might think, I can see a common factor here, so it's kind of obvious. If you're looking at a quadratic form, then maybe there's an obvious factor. But to look at one of these and to just see it feels a bit less likely. What would I do? You kind of have to find the you're going to find the not equivalent form which has that factor removed. You can do it. You can do it. That's sort of the point, that you can do it. But we don't have very good technology, do we, for getting from this form to this not equivalent form over here. If you look at this one, you're good, because you spot, everything here is a multiple of 3. Can you work it out by looking at lots of corners? What can you do to compute this thing? If you start with the topograph, your 3 values. I don't want to say you can't do anything, because I mean, in some sense, obviously you can. You can work out delta and then just divide it by some squares, trial and error. Can you embed that algorithm somehow into just looking in the quadratic form? I don't know. Not sure. It's 218 case. 218 case. You've got this problem that, well, actually none of those are multiples of 3, so good luck everyone. I mean, then you're going to say some combination of these, because of course you can, from that you can generate the number 6 minus 63 and then be happy. B squared minus 4, so 1 minus 4 times 2 times 8. Yeah. I think we should be looking at these forms, because these are the tricky forms, the ones that are hard to identify, not the non-primitive ones on the right. Well, I mean, there's 2 sorts here, so you could still be caught out, right? There's 2 times 103 form. The answer is now 4. That's obvious. Not everything it makes is a multiple of 4, but 103 itself has some conductor to its discriminant, because it was not equivalent to, but has the same discriminant as this non-privative form. This is a good workout for me, I think, because this is helping me remember the links between things. What could you do? Given 3 numbers at a point and you don't want to calculate delta, could you do something else to identify? I think that delta has. It sort of is asking to convert it to one of these, right? Define like B. It's a property of the discriminant, not a property of the form you're looking at, really. Don't know. Ooh. Throw Harry Potter. Are we now just sharing Harry Potter merchandise? Of course we are. Yeah, we're now just sharing Harry Potter merchandise. Other people with glasses are available. I'm not even sure I look like Harry Potter, but there we go. Right. Does the GCD of A plus B minus C, GCD across all of the points in... So A plus B minus C is what they call H, the H value. On a particular, it's property of an edge, really. So if you're looking at a value, it's kind of, you can associate it with an edge. So then if you look at the GCD of all the H's, all of these things, I don't know. Oh, Spider-Man, great. But I have glasses. It's not like Peter Parker at all, right? That guy. Hang on, let me just Google pictures of Spider-Man. I want pictures of Spider-Man. Yeah. Wait, the previous one? Anyway, never mind. Look, not important. Not important. I don't know what to take the GCD of. I've got one value of H. If I take the GCD of that over all points, no, I don't think this is doing anything, is it? if there's some big square that divides this, if there's some big square that divides this, then will you eventually find that it divides this as well? It might not divide P or Q, so I'm not really sure why it would divide H at all. Instead of looking at some random ones, I'm going to look at some of these. I'm going a bit long? Going a little bit long. Fair enough though, that's what we do. I'm going to use your diagram though. Here we are. So I want to look at one of these ones. Like, for example, the 108 one. The 108 one. So the question, I suppose, is can you detect from this picture, 108, that the correct conductor is 2? Oh, A plus B minus C, you can read in 3 different ways. So if you get 3, if you're looking at 3 edges, maybe that's what you mean. Looking over any, there are lots of ways you could choose A plus B plus C corresponding to all of the edges. Maybe you mean over all of the edges. So in this picture, A plus B minus C, at any corner, it looks like there are always 2 odd numbers and 1 even number. That is true, isn't it? So then would you look at that and say, the GCD of A minus B plus C is 2? It's worked. For any 3 in the whole graph. Yes, for any 3 edges. I think you're asking, does the conductor divide H? All of the H values. So that then you could choose some of these things. If you're saying any 3, then I'm going to... does that mean that D is even? Is a harder question than is D even. So D is 2 for this one. And it looks like all of the H values are even. Oh, they have the same parity. We know that. Because the discriminant, no, not the conductor, the discriminants and the H values have the same parity. The discriminant and its conductor might not have the same parity. If you perfectly remove the fact it's a 4 from something of the form 4 times an odd number. Okay, right, maybe that's a good case then. 4 times an odd number, so let's do the 103 case. I don't know what I was doing. What was I doing? So this is another case where the conductor does divide everything. Conductor is 2 again. Can I have a more interesting conductor? 48? 1A12? 1A12, maybe 304 would be more fun. .304 feels good. Okay, so 304 is a case in here. It's got discriminant minus 48, and the conductor is supposed to be 4 because you can divide by this to get minus 12, which is another discriminant with the 103 case. It's equivalent, not equivalent, but another form of the same discriminant is to 103. So we're going to find something that's 4-ish about this picture, which, oh, it's 16, look, something 4-ish. And now I'm in trouble because if I do 16 minus 16 plus 3, take away 7, 12. 7 plus 3, take away 4. Okay, 7 plus 3, take away 4 is 6. Yeah, 7 plus 19 is 26, take away 4 is 22, which is even. It's got the right parity, so I think we're onto something there, but I'm not generating. If I do the A plus B minus C thing, these H values, like for this one is 26 minus 4, it's 22 for the value here, which is not giving me vibes of conductor. It's GCD2, but unfortunately the 304 case is here, where the conductor is actually 4. So I think we've got something with parity going well, maybe, but I'm not convinced at the moment that GCD of the H numbers. I can't see why the GCD of the H numbers would be anything, but what do I know, I suppose. Looking at this edge, we get 10 take away 6. 10 take away 4 is 6. This arithmetic progression goes 4, 10, 16. And 6 is even, but not multiple of 4. I was having really understood. So the H values are of course related to things. If you see two values like that, 7 and 3, then H squared take away 7 times the H squared. 6 squared take away 4 times 7 times 3. 36 take away 84 or something. Something like that. Thirty-six take away 4 times 7 times 3. 36 take away 84. What did I say it was supposed to be? Minus 48. Yeah, I can't maths right now. 48. I'm trying to work out, is 36 take away 84 minus 48? It might be time to call it a day. 36 take away 84 is that minus 48. How can I work that out? Oh, I could do. I hope it is. Minus 48. Well, I could do is 36 plus 48 equal to 84. Yes, it is 70, 84. Good. I think that's it. That's the sign I should stop. I think we've seen some quadratic ones. That is a counterexample, right? We did a counterexample. This edge here. So the GCD of something involving a plus b minus c, 7 plus 3 minus 4. So anything involving the GCD of that, 7 plus 3 minus 4 is 6. So GCD of that and anything else. Greatest common divisor. Well, it's only 4 because 6 is not even a multiple of 4. This edge is the value of 6 for a plus b minus c. So I think that's a counterexample to the conjecture. You're on the minus 63 one as well. Okay. So I'll put in 218. 218, and the correct answer is supposed to be 3. And now we've got 13 take away 8 is 5. So I'm not keen. You said the GCD divides D. This one's worse then, right? Because now 11 plus 2 take away 8 is 5, which is kind of nothing to do with 3 for the 218 case. Right, okay. Mary's hurt. Mary's injured. One of our top chat people is injured from chat. 1 divided 3. Yeah, the GC div. Oh gosh. Oh no. I see what you mean. Right. You're telling me that if I work out the GCD, then I'll get 1, and then the conjecture is that divides the conductor. That's 2 steps removed, isn't it? I thought you were trying to calculate the conductor. You're telling me that something that might be 1 divides the conductor. Maybe. I don't know. It's more trivial. It's just like, it's got an extra wrinkle that makes it harder to engage with, which is that we're no longer quite talking about the I was hoping that we would get an understanding of the conductor and less interested in understanding of the factor of the conductor, especially because no, I'd still be interested if that were true. Cool, right, look into it. Okay, right, we're going to call it there, I think, for Twitch streaming. Thanks for joining in. Thanks for your help with the maths. I will see you next time for, what are we doing next time? We're waiting until the next chapter. No, we read this, it was good. We got there, there was some squares going on. We even read this bit down the end, and we had a look at, yes, we finished the section, didn't we? We had a look at this version of like a Euclid's theorem sort of thing. We skipped all the exercises because that's chill. We should probably do the exercises. Yeah, maybe on a reread. So next time it's genus and characters. This is where we're at. I'm going to draw a bookmark. There you go, I coloured it in this time as well. No, good. Right, okay. I think that's it. I'm ending the live stream. Bye everyone.